Welcome to the buffer calculation tutorial. In this tutorial, we're actually only going to cover one type of problem. So, let's consider some of the things that I'd like you to focus on before we start the problem. First of all, keep in mind the dynamics of a buffer system. Keep in mind that there's a weak acid and a conjugate base. Before we start the problem, I also want you to think about where did the concentration of these two substances come from? The concentration of the weak acid and the concentration of the weak base. Especially focus on where the concentration of the weak base came from. This is especially complicated. In addition, I'd like you to focus on the issue of volume in this problem. It's a bit complicated, so pay close attention to how it gets explained in the tutorial. Also, before we get started, I want you to consider what happens when you add an acid to a buffer system and what that does to the concentrations of the weak acid and the conjugate base. This is also important in the problem.
A buffer contains 1 molar acetic acid and 1 molar sodium acetate. The Ka of the acetic acid is 1.8 times 10 to the negative fifth. Calculate the pH of this buffer. What will the pH of the buffer change to if 0.10 molar HCl is added? Let's take a look at the first part. Calculate the pH of this buffer. To do that, we need to identify the concentration of the acetic acid and the concentration of the acetate conjugate base. In this case, the concentration of the acetic acid is very easy to identify. It's given to you right in the problem. It's equal to 1.0 molar. The concentration of the conjugate base comes from the sodium acetate. Because sodium acetate completely dissociates, the molarity of the sodium acetate will also be the molarity of the conjugate base, the acetate ion, C2H3O2-. The next thing we need to do is calculate the pKa from the Ka. This is only important for buffer problems, and that's why I don't emphasize it in other situations. The pKa, just like the pH or the pOH, is calculated using the negative log of the thing that you're looking for. So in this case, we have the pKa equals the negative log of the Ka. Having done pH problems and pOH problems, this should be very simple. So we take the equation and we substitute the value of Ka. This gives us that the pK equals the negative log of 1.8 times 10 to the negative fifth, which equals 4.74. Notice that everything is unitless. The Ka is unitless and the pKa is unitless. Now that we know the pKa, we can use the Henderson-Hasselbalch equation. This equation requires the pKa. The pH of a buffer solution will be equal to the pKa of the weak acid that's in the buffer plus the log of the concentration of the conjugate base divided by the concentration of the acid. Now that we have this equation, we can easily substitute the concentrations in. Notice that above I identified which thing was the acid and which thing was the conjugate base. This should make it a little bit clearer as to which molarity goes where. It wouldn't really matter for this problem being that both concentrations are 1.0 molar. So now that we've substituted the numbers in, we have that the pH of this buffer solution equals 4.74, which is the pKa value that we calculated before, plus the log of 1 divided by 1. Clearly, the log of 1 divided by 1 is just the log of 1. And if you can remember your math, the log of 1 is 0. If you didn't remember that, you could actually just put it into your calculator and you would get a value of 0. Therefore, when you add 4.74 to 0, you clearly get 4.74. So the pH of this buffer solution is 4.74. Now let's take a look at the second part of this problem. What will the pH of the buffer change to if 0.10 molar HCl is added? The first thing we need to do to solve the second part of the problem is identify the fact that if we add a strong acid to this buffer solution, that's going to increase the concentration of the weak acid due to a shift in the equilibrium reaction that the buffer system contains. Therefore, the concentration of the weak acid, in this case acetic acid, is equal to 1.0 molar plus 0.10 molar from the HCl, which equals 1.1 molar. The concentration of the conjugate base conversely decreases due to the increase in the strong acid. Therefore, the concentration of the conjugate base equals 1.0 molar minus the 0.10 molar acid that was added, which gives us 0.9 molar. Next, we substitute those new values into the same equation that we had before. The pKa stays the same, so we have 4.74, and in this case we add the log of 0.9 divided by 1.1. This, of course, will change our pH of the buffer system. Which direction is it going to go in? Clearly, adding an acid is going to decrease the pH of the buffer, but notice how little it changes. The value after you do the calculation is 4.7. Adding a strong acid to a weak base buffer like this only decreases the pH by very little, and that's what buffers do. They are able to resist a change in the pH.
Now that we've completed the problem, the last thing I want you to look at was the significant figures. Notice that the value of the pH went from 4.74 down to just 4.7. Why did the significant figures change from 4.74, 2 places to the right of the decimal, to just 4.7, only 1 place to the right of the decimal?